Hi everyone. I thought that we could talk about buffers in the lab today, so I want to do a little demo for you. In this beaker, I've got some deionized water, roughly, I don't know, 250 mils or so, and in this other beaker, I'm going to pour some buffer. And I don't know if you can see the label here, but it's a buffer containing acetic acid and sodium acetate, or you might think of that as a buffer containing HA and A minus. So I'll again pour roughly 250 mils, just like the water. And now I'm going to add methyl orange indicator to each beaker. Methyl orange is usually yellowish under basic conditions, and then it turns pinkish or red under acidic conditions. So maybe 5 drops to the water and 5 drops to the buffer. And let's give these a little stir. So I hope you can see that faint yellow color. I hope it shows up on the camera. And now to each to each solution, I'm going to add a strong acid. I'm going to add 0.1 formal hydrochloric. Hope you can see it there. And we'll see which solution stays yellow longer. So here we go. 1 squirt to the water. Ooh, I see some pink there already. 1 squirt to the buffer. I think that water may have turned already. Yeah, that water may have turned. Let's keep adding acid to the buffer and see what happens. Another squirt, no color change. And another, no color change. The buffer doesn't seem to be changing pH. I bet I could pour the acid into the buffer and it still won't change color. So I hope this demonstrated to you what buffers do. They're solutions that resist changes in pH because they have solutes inside that can neutralize the acid or the base that we add. So we'll go ahead and write a neutralization reaction for what we just saw here. I hope you enjoyed watching how that buffer resisted that change in pH, especially compared to water. Again, the buffer I used was a buffer containing the weak acid acetic acid, and the salt that was the conjugate base was sodium acetate, or you can think of this as HA and A minus. But there's another type of buffer, a buffer containing a weak base, for example, ammonia, and a salt with the conjugate acid, which would be ammonium or ammonium chloride. You can think of this buffer as containing B and BH plus, and this is the buffer I think you used in lab that had that strong ammonia smell. But this is the buffer that you saw me demonstrate with, and I said that we were going to write a neutralization reaction. So remember in that demo, I was adding a strong acid, and the buffer contained HA, acetic acid, and A minus. So which one of these solutes do you think neutralized that H plus? Well, it would have to be A minus because HA is already fully protonated. So the neutralization reaction we could write is H plus got neutralized by A minus to form HA. And if you think about this equilibrium constant, if you look closely at this reaction, isn't this just a Ka reaction flipped? Right? This would be a Ka reaction, and isn't the neutralization reaction just the Ka reaction flipped? So the equilibrium constant would be 1 over Ka, and if you looked up the Ka of acetic acid and took the reciprocal of it, you would get an enormous number, something like 5.7 times 10 to the fourth. That is huge. And all equilibrium constants for neutralization reactions are going to be enormous. So for that reason, we think of neutralization reactions as going to completion. I think that's worth writing down. Neutralization reactions go to completion. So we're going to do three types of buffer problems, calculating the pH of a buffer, and you'll probably use the Henderson-Hasselbalch equation to do that. And then these two. The buffer in action is a lot like that demo I just did. The action of a buffer is to resist changes in pH, and then we'll also do a problem on preparing buffers, but the very first step in both of these problems is to write a neutralization reaction like we just did on the previous slide. And do you remember how H plus was a reactant in our neutralization reaction? That's always going to be the case where H plus or OH is a reactant.